First, I'd like to thank the organizers, Kathy, for hosting this event and for organizing it and for inviting me to speak. I'd like to thank you for coming as well. And I'd like to thank my co-panelists for illuminating talks. I've learned a lot about the human dimension of this disaster. And what I'd like to do today, in this brief period of time, is to give what simply can't be a comprehensive accounting of what we know about the extent and the impact of the disaster on the marine environment in 15 minutes. But I will choose to talk about some of the measurements and what the scientific community, and specifically the oceanographic community, knows about the concentrations of radionuclides released from Fukushima in the North Pacific, and then what health physicists and health professionals that specialize in radiation and radiation doses say about what the likely impacts of those concentrations are potentially on the public and the marine environment here off of BC. So to begin with, I need to talk a little bit about how scientists talk and how it's confusing sometimes. When we talk about radioactivity, we use different sorts of measurements, and I just want to familiarize you with one in particular that I'll use today, and that's the becquerel. So this is a measurement of the amount of radioactivity, the number of atoms decaying per second in amount of material. So 1 becquerel is 1 disintegration, 1 atom that is radioactive decaying per second. You may have also heard of units called disintegrations per minute, DPMs. These are the sorts of measurements that you typically get from Geiger counters, for example. So a DPM, disintegration per minute, 1 becquerel equals 60 DPM. So I also want to talk a little bit about how much radioactivity exists in seawater. About 97% of the radioactive decays that you measure in a volume of seawater occur because of naturally occurring radionuclides that have been brought to the ocean as the continents as the continents weather over time. They've been with us since the planet was formed, or they're formed in the atmosphere through reactions that happen there. About 7% of those decays that you can measure in that volume of seawater come from radioactive elements that have been added through human activities. And that's atmospheric weapons testing primarily, our nuclear disasters, Chernobyl and Fukushima, and also reprocessing of nuclear fuel. And so on average in seawater we have on the order of 14,000 becquerels per cubic meter. So that's 1,000 liters, or 14 becquerels per liter. I just want you to keep that number in mind as we move through. Now, in terms of how radioactive elements were delivered to the ocean from Fukushima, and I will focus on just the ocean today, but it's important to note that many radionuclides of significance to their radiological impact on health were released in large amounts, cesium-137 and cesium-134, strontium-90, but it's also important to remember iodine-131, for example, the iodine isotopes. It's important to remember that virtually every element that you would find in the fuel and at the plant, some amount was released to the environment. But I'm going to focus in primarily on cesium, the cesium isotopes, and on strontium-90 today in my presentation. There were releases to the atmosphere whereby significant concentrations were released directly to the atmosphere when the plants exploded, the hydrogen explosions that occurred at the site. Those radionuclides were distributed around the globe. Okay? They were detected by the Comprehensive Test Ban Treaty sensing sites around the globe. There were direct releases to the ocean resulting from seawater being used to infiltrate and cool the site, which brought radioactive elements directly into the ocean. These releases were very high in the few weeks following the disaster. They dropped off dramatically, but they continue today, as we heard from our previous speakers. We also transport radionuclides from the disaster that were deposited on the Japanese mainland through rivers. And currently we also have groundwater that's infiltrating the site and moving through the soil and being deposited and infiltrating the coastal zone. So these releases continue today, and they're happening at lower absolute rates, which affects the concentration in the ocean, but they continue today. This is a plot that shows the concentrations of cesium-137 and 90 strontium close to the coastal zone immediately next to the Fukushima reactor sites. This runs from March of 2011 through to February 2012. And what I want you to take away from this particular figure is that an international consortium of scientists are measuring the concentration of these radionuclides released from the site. This is a logarithmic scale. Each one of these major units is a factor of 10. So immediately following the disaster, we see very high concentrations of cesium-137 corresponding to this very significant pulse of radionuclides that came from the site post-disaster. We see strontium-90 being released also in relatively high concentrations, but roughly a factor of 100 initially less than cesium-137. You see an exponential drop-off of the concentrations in the coastal zone as that slug of radioactive material that was added to the coastal ocean is mixed and transported away from the Japanese mainland. The prevailing currents are bringing it towards our coast, and this is what I'll begin to talk about. But what we want to take away is that the relative concentrations in the coastal zone have leveled off, and recent measurements that were reported to me at a recent meeting a couple of weeks ago, these concentrations haven't changed up to this point in early 2014. So they've leveled off and they remain relatively invariant. So the bulk of the radionuclides that have been added to the marine environment occurred in the weeks following the disaster itself. To put these releases in perspective, I've made this figure where the area of the circles that you see correspond to the amount of radioactivity in petabecquerels, which is a really big number, 10 to the 15 becquerels. The blue represents cesium-137, and the light colors represent strontium-90 from human releases of these radioisotopes to the environment. And you can see that atmospheric weapons testing during the 50s and 60s primarily resulted in a very large amount of cesium and strontium being deposited into the oceans. We see smaller amounts from leaks or discharges from plants like Sellafield in the UK that are reprocessing fuel. We see that Chernobyl added a significant amount of cesium-137 to the ocean, but virtually no strontium. And then we see the 70 petabecquerels that have been released from Fukushima and the correspondingly low amount, roughly a factor of 70, perhaps 100-fold low, at least 30-fold lower of strontium that's been released to the coastal ocean. So this is just to give you some scale with respect to what human sources of these radionuclides have been to the ocean. Now, as I pointed out, the releases to the coastal zone have actually been mixed and diluted and transported by the prevailing currents from Fukushima. And these are modeling studies that physical oceanographers use to determine the dispersion and transport of those radionuclides in seawater that behave as dissolved substances towards our coast. And what we have are two main models that are predicting the arrival time, slightly different arrival time, and a range of potential concentrations. And this depends on how well the models actually parameterize or explain what's actually going on in the ocean. And so the predicted cesium-137 off BC varies from about 1 or 2 to 30 becquerels per meter cubed. Now, that's very different than those huge, very high concentrations close to the Fukushima site early in 2011. But this range of values is important to keep in mind, and it's the measurements that we're making now, the oceanographic community, which are helping to determine which of these predictions is likely. And it's the concentration of these radionuclides that will actually determine the impact on the marine environment, organisms there, and people like us that rely on the ocean for our food and for our recreation. So the Canadian government, the Department of Fisheries and Oceans, and specifically Dr. John Smith at the Bedford Institute on the East Coast, have been monitoring the concentration of these radionuclides in the Northeast Pacific Ocean along the Line P program, which is run by Marie Robert at the Institute of Ocean Sciences here in Sydney. So since the disaster, they've been going out and making measurements of these radioisotopes from the coast of British Columbia out into the middle of the Alaskan Gyre. And what have they found? Well, basically offshore, the plume arrived in June 2012, and in June 2013, concentrations of cesium-137 that are attributed to Fukushima. We can do this by using cesium-134 that has a very short half-life and must have come from Fukushima and not atmospheric weapons testing or Chernobyl, for example. And we see concentrations of about 0.9 becquerels per meter cubed to 0.3 becquerels per meter cubed in the coastal zone. So higher offshore as the plume is moving in. So these concentrations are more consistent with the lower end range of that modeled range that I gave you before. Okay. The plume arrived a little bit earlier than one of the models predicted, and the model that got the timing right got the concentration much too high. So there's some information here for physical oceanographers, but the point is that the plume is in our coastal waters at this point, and these concentrations of 0.3 to 0.9 are going to increase as the heart of the plume, that slug that was added to the ocean in early 2011, arrives over the next year to 2 years. And so the question is, how high are the concentrations and what does that mean? So that's exactly what I'm going to address now, is what do these sorts of concentrations and concentrations within the range that are being measured in the seawater and in marine organisms mean for you and I living here? What sort of risk is associated with these radionuclides in the environment? So, for example, if you consider a Pacific salmon, and we've got radioactive elements that are in seawater, the exposure of this animal and its body burden of radionuclides results both from uptake from the seawater directly, but then also accumulation, bioaccumulation of these elements that are dictated by their chemistry, which is different for different radionuclides, as it passes through the food chain and ultimately into the salmon. So if you look at fish, they concentrate, the net result of both this dissolved and food source of radionuclides to the fish, for cesium results in 100 times the concentration per mass in the fish compared to the concentration of the radioisotope in the seawater. For strontium-90, that factor is about a factor of 3. So for a given concentration or equal concentration of cesium versus strontium, you'll get about 30 times more cesium-137 than you get strontium. So what I'm going to do now is to take those concentrations and convert them into a dose, an effective dose. So how does the radioactivity impact your body? Okay. And these effective radiation doses for a year, they take into account the type of radiation, whether that radiation is internal or external to your body. Have you ingested the radionuclide? What organ that element tends to target? And then the impact of that element is integrated over a 50-year time period. So this is called an effective radiation dose. Now, alpha particles, alpha radiation, are very large and slow, and they can't penetrate your skin, but if you get them inside your body, inhale them into your lungs, for example, like plutonium, it can cause significant damage. So its weighting factor, if it gets in your body and in your lungs, increases your effective dose. Beta particles are less massive, but they can penetrate the skin, and they have the potential to cause damage, but not as much as an alpha particle. Gamma rays are high energy. They can go right through your body. If they hit something, they can cause a problem. So basically, we take into account the type of radiation, alpha, beta, or gamma, whether it's external or internal, the organ that's exposed, and then we talk about the potential impact of that isotope over 50 years. Now, this is the effective radiation dose from eating salmon or fish, 60 different fish that have been analyzed so far, with the area of these circles corresponding to the effective dose for a year in microsieverts. And this is just the unit we use to describe these things. And this is assuming that you eat 20 kilos of fish a year, which is perhaps a little bit more than the North American average, around that. So if you look at the effective dose that one receives from cesium that comes from Fukushima in these fish, it can't be detected at present. It's below detection limit. But if we assume that it's present in all the fish at the detection limit, you calculate a dose of less than 0.8 microsieverts. Now, the naturally occurring isotope polonium-210 that's produced by uranium decay in seawater is found at concentrations that lead to a significantly higher, about a factor of 10 to 20 higher effective radiation dose from consuming fish. So if you consume these fish with the level of cesium that's present from Fukushima, the amount of effective dose you receive and the potential health risk is on the order of 10 to 20 less than the naturally occurring polonium that's always there in the fish. Now, as I move through the next couple of slides, the scale of these circles will change to account for increases in exposure. If there are any smokers in the room, if you smoke a pack of cigarettes a day, the amount of effective dose that you receive from polonium-210 and other radioactive elements that are present in the tobacco, just from the plant accumulating it from the environment, a pack a day gets you about 360 microsieverts. Or you would have to eat 20 kilos of salmon a day to get the same dose that you receive if you're smoking a pack of cigarettes a day. And again, the size of these circles shrink relative to natural background radiation. So just based on our source rocks that you live around that have naturally radioactive elements in them, you breathe some radioisotopes in. You can see the range between Vancouver, Victoria, and Winnipeg, which is basically the range of natural radioactivity that we see in Canada. And again, the amount of radioactivity that you get from eating your 20 kilos of fish a year from Fukushima isotopes is about a factor of 2,000 less than what you receive just from walking around and breathing and eating. So just to summarize really quickly, the radioactive releases from Fukushima to the ocean were greatest in the period shortly after the disaster. Currently, those release rates that fix the concentration in the coastal zone and what will be transported across the Pacific are on the order of 10 to the 4 to 10 to the 5 times less today. Radioactive plume arrived offshore in 2012 and inshore last year. We're waiting on samples that were collected just recently. The concentrations in seawater and fish do not appear to represent a significant radiological health risk compared to other sources of radiation that people are exposed to. And we need to monitor over the next few years to constrain what the maximum concentrations will be in there for the impacts. So especially because conditions at the plant could change and release rates could increase. And if they increase to the way they were in 2011, that's a concern. Now, I just wanted to point people to some sources of useful information. Ken Buessler's website that gives information on his monitoring program, and also some really great monitoring data that exists through Health Canada. And thanks very much.